Yes, sir.
Okay, so we have come to the very important part in transmission line theory, uh, which is one of the fundamental aspects of transmission line theory as well as the microengineering. That is Smith chart. Okay, so we are going to discuss the Smith chart and the basic configuration, uh, how it is constructed all the way. Then we will see the applications of them. The primary applications of them is uh, matching. Okay, so we are going to utilize that uh, Smith chart for various applications, particularly to match the source and load and match the transmission line and the load. Like there are several aspects are there, and not only that, we can even predict the impedance at any particular point in the transmission line. So many advantages are there. So the basic transmission line theory try to describe the overall transmission line as a RLC equivalence, and by the way, we can even define the impedance of the uh, transmission line with load or without load, and how it is matched with the transmission line. Everything can be described by the transmission line theory, and this theory is so successful one, and nearly about more than 100 years this actually used practically in various aspects. Okay. And this theory is so also it is considered one of the accurate theory. We will see the accuracy of it aspects and the simplicity of it when we see the real problem is solved. Okay, so I think we already covered up all these part. We will skip this one. So the basic idea of the transmission line theory is to describe the impedance function of the transmission line with which is connected with a load and a source. So this is a very important picture. So this is the entire problem is simplified here. So as I already told, this transmission line theory comes for only for high frequency applications like frequencies of more than 500 megahertz. Okay. So after that particular frequencies only, we will see the reflections due to impedance mismatch, and then traveling in a particular direction, and it see the difference between the impedance of two different medium. All these things are attributed only at high frequencies. If you notice, you just ask any engineering student who are working in at any case, they never know that there is a concept called reflection, and due to this reflection these many issues are coming like that. It is the reason is that those signals, they are operating at very low frequency, and even if they are so this is the fundamental problem in transmission line concepts. Noise is coming. Okay, now so this particular problem, we have described the voltage at any particular point and current at any particular point. Okay, so this is actually described in terms of uh, the incident and the reflected components. Okay, and often this will be normalized by the characteristics impedance of the transmission line, because we, this both incident voltage and reflected voltage can be representing both voltage and currents. So this is most important reason that it often normalized by characteristics impedance. So this is the overall aspect, and we worked out for deriving the expression for the input impedance, and this deals with the length. So when the length changes for the terminated load impedance, the input impedance will change. Now the question is, what will make the this value equal to z naught? Okay, so this is very important question, because when this value is z naught, and here also we get the input impedance as Z0, and obviously whatever the load it may be, all the power will be transmitted provided this Zs is also equal to Z0. So everywhere the impedance is matched. So since the impedance is matched, we will get the maximum power transfer. So that's the ultimate objective of the transmission line technique, means the, in other words, application of the transmission line theory. Okay, so that is what described as a function of reflection coefficient. Alternatively, this can be described in terms of standing wave ratio. We have seen some examples how to calculate those values, and we also have seen some special cases in the transmission line that if it is terminated by a short circuited line, if it is terminated by a open circuited line, so we could notice that it will immediately give a reactive impedance, which means that this can be either a capacitive or inductive or both can be applied there. And when we draw as a function of the electrical length beta L, then we will get the distribution of the impedance as a step-like function. This often referred as impedance harmonics. You can see this, the impedance whichever is seen here, again it repeats. So this repetition property with respect to beta L, which corresponds to the frequency again. So the frequency also you will see such a harmonics. We can notice such a behavior in this. For instance, if you see with respect to Z or beta Z or beta L, whatever it is, we can see this, the reactance is keep on changing. The same behavior is repeating. So due to this particular reason, you can see that even though the system is designed for a particular frequency of naught, it is repeating and you will get at its corresponding harmonics. Okay. So this particular harmonic property clearly proves that the theory is correct, and or whatever the mathematical description, whatever we have, which we call theory, is so accurate. Okay. So this is why if you see the people who are working in microengineering or RF system design or micro integrated circuit, that is the entire IC which is used to design modulator and demodulators, those kind of systems we call MMICs, that is monolithic micro integrated circuits. So those all circuit designs, people often use this transmission line theory because we can achieve almost any possible capacitance or inductance value we can achieve with simply defining the length. And not only this, we can have parallel combination. At any particular point, we can have parallel combination of short circuited line and open circuited line. Like we can create any lines. So this solely we have to apply the circuit theory, which is commonly used for parallel and series combinations. And the condition for matching is very important one. You have to always keep this in mind. Then we have seen the quarter wave transformer, how it is helpful in matching two distinct impedances. One system is having impedance of Z0 and another load which is having completely different impedance. Let's say this is an antenna. So this antenna might be having let's say 100 ohm, and this is a 50 ohm transmission line which is supposed to be connected by a receiver. Okay, so from here the signals are received and it's supposed to go to here. So this is the basic problem. So now we have to make a impedance transformation by using a quarter wave transformer. So this quarter wave transformer of length lambda by 4 with the characteristics impedance of Z1 can simply transform this impedance to this without any issue. So the impedance will be matched. So when you look at the input impedance in the quarter wave transformer, we will simply get is equal to Z0 will come, which is the expected impedance at the source side. So that is what the advantage of that. So for this, what we have to do, we have to choose the characteristics impedance of the quarter wave transformer like this. So uh, for several years, actually, quarter wave transformer is more than sufficient for many impedance matching aspects. But this is, if you carefully see that this is supposed to be a resistor. Okay, so this is supposed to be a real value. So if it is a complex number, it is very difficult to design, and you can cancel out only the effect of the real or the resistance term due to mismatch. But the reactance one is very complicated one to address it. Okay, so this was, I'm talking in 1910, 1910, 1920, like that, almost 100 years back. Okay. So people have come up with quarter wave transformer is one of the, almost it is successful even till date. Actually, it is used for. So this is the overall summary of the transmission line theory in terms of the impedance function it is described. So if you notice that the impedance will be written in terms of uh, uh, reflection coefficient, and sorry, the impedance is used to define the reflection coefficient, and reflection coefficient is used. So they are highly connected. In many places, people used to say that the impedance is nothing but reflection coefficient, and vice versa, like that. And in during this telephone era, and even after that, when the modern telephone exchange has come, this transmission lines actually become inevitable structure. Nearly 100 years, this transmission line theory is used for successfully connecting the users from one place to another place. So, and everywhere the impedance will be completely different. So the telephone exchange primary problem is making the good communication. So this good communication needs a successful matching network design. So it is always very difficult to address the problem. If there is a big problem, then you just imagine that nearly about kilometer length we have to take the risk. So this is always a problem. So uh, and at that at those times, very few labs were being very successful, like Bell's lab, and another popular lab is mm, just named after the professor of coding theory. Um, okay, so there are about maximum in America about 5 to 6 labs. One of them is most popular one is Bell's lab. I think many of you heard about that. So in these labs, only telephone exchange related research were going on, and at those times, they found this problem is keep on repeating. So they need a calculator. So the calculator at those times they thought of making as a computer based, like yeah, logic gate based. And by the way, when they put some input, it immediately will tell what is the impedance value and what's supposed to be the matching network design, all these things. So they were very confused how to program that all the way. But there is a person called Adam Smith. So he has come up with very interesting idea, that is what we call as Smith chart. So this he has come up with the he is a very brilliant mathematician. He converted all the impedance or the reflection functions as a circle equations. So these circle equations, not like a regular polar chart or something, they are often referred as concentric circles. So you can see, notice here that here the center point of the concentric circles are actually keep on will move. So you can see that there is a circle here and another circle here. So like that. So this is actually the nature of the chart, and it has two circles. One is real circles, which describe the resistance part. You can see that they are called real circles, and similarly imaginary circles, like these circles will be coming from the external edge. So in fact they're supposed to be like this. So they are actually orthogonal circles, exactly orthogonal to the rest. So this one circle is moving this side, these circles are moving in the orthogonal side. Okay, by combining these two or combination of this real and imaginary circles, the Smith chart is invented. And the Smith chart is people used to say it is more than a computer. So in fact you can accommodate almost infinite possible impedances. And the interesting fact behind this impedance theory is uh, you can have n number of actually almost infinite possible impedances are there. and we have another system called characteristics impedance. So, and the final one is the reflection coefficient. If you notice this three, this has infinite possibility. This is from 0 to 1. Okay, so considering this interesting fact of the reflection coefficient, Smith has reduced this impedance problem into reflection problem, and this reflection coefficient is written in terms of circles. So this circles are mapped to represent all the real part and imaginary parts of the reflections or the impedance. Even we can utilize this same chart as the reactance chart. So what we have to do, simply we have to do the inverse of that. Okay, inverse means the circle supposed to be put this way. So this is the circle, we have to put the circles in this way. Just if we rotate about 180 degree, you will get the admittance chart will come. Okay, so this can be used as an impedance chart or reflection chart or admittance chart, and in upcoming days it is used for plenty of descriptions. Present day microengineering, if you see that, if you can easily understand almost all the system properties if you directly use the Smith chart. Many people see this Smith chart as a tricky one, but it is not. It is very simple and very humble chart. Okay. Moreover, it is the only chart or the for EC student. Only this chart means, I'm really sorry. Smith chart could be understood only by EC student. So if you are studying this, you can yourself call that as a special one. Because many people do not know what is Smith chart at all. It happens often that in the invigilation hall, we will ask for Smith chart, they will bring polar chart. Then we will tell, no, this is completely different. And we generally used to draw the chart and we will say that the chart look like this, come and bring it. So, and this is only EC student can do that. Like mechanical students, they use some notebook, is it for some tables or something. So similarly, Smith chart is very special for EC students. So this could be used to map any impedance or any reflection coefficient. By the way, we can even move along the Smith chart. So we can move along the Smith chart from one place to another place for the given electrical length beta L. Okay, so we will see this how this chart is constructed, and we will see some example how to map the impedance and the transmission line problem into this. So we very well know that the reflection coefficient is the function of the impedance, and this has two things. One is the complex part, that is the magnitude part and the phase term, as well as the real and imaginary part is available. Therefore, this real part can be described in terms of impedance, and the real part can be defined in terms of impedance. Okay, so this is what the overall aspects of the reflection coefficient. Similarly, we have the load. This load actually can be represented as a function of so for instance, if you can divide this numerator and denominator by Z0, you will get Z0 by ZL by Z0 minus 1 divided by ZL by Z0 plus 1, which is nothing but the reflection coefficient. So now what we are going to call this Z0 by ZL as small ZL. Small ZL you can call all the time. Okay, throughout the course, it can be assumed as the normalized impedance. So this normalized impedance can be written with real and imaginary part, which can be rearranged by this real and imaginary parts. So you can see that the impedance now it is written as the real and imaginary part, and in terms of reflection coefficient, whose real and imaginary parts are again used. So by this way, the impedance, which are real and imaginary, can be represented by real and imaginary part of the reflection coefficient. Now there is a now we can do one thing, that we can isolate the real part and imaginary part, and we can make and by rearranging the terms we can get the circle equations. So that is what the work being done by Smith. So this is the real part and this is the imaginary part. Okay, it is very simple that you have to take the numerator denominator multiplication and you will get it. So this is the real part and the imaginary part. This equation is converted into circle equations. So in this circle equation, this is the function, and so this is going to be the so what you see here is the right hand side one is the radius, and this is the function, and this is going to be the corresponding orthogonal function. And similar way you can see here, this is the function, this is the orthogonal function, exactly opposite of that. When you take the square of that, you will get 1, and this is going to be the radius. So like this two equations being developed, and since these two equations are orthogonal means their position. So this is the x and y axis, this is the x and y axis. So you will get two set of circles. One circle will follow x axis, another circle will follow y axis. So the real function will follow x axis. So you can get circles like this. In fact, it is true that in the minus x direction also it is quite possible. When you take the magnitude of that, you can remove that. So you can have the circles here, and similarly for the imaginary part also you can have circles in this direction. This derivation is available in many of the books. I'm not sure whether it is available in StudyQ or not, but anyway I will try to supply the detailed derivation from this to this. I'm not sure whether this is required to study in depth, but those who are having curiosity in understanding this Smith chart, definitely we can study upon it. So what is the next job is we have to draw the real circles and the imaginary circles. So the real circle is nothing but the real part of the impedance or real part of the reflection coefficient, which is written as the equation. And you can see that this the radius has the +1 term and r by 1 plus term. So due to this two distinct behavior, the radius will keep on increase. At the same time, the position of the center of the circles also will keep on move. Yeah, this is the center. This is the radius. Yeah, the center and radius is clearly given here. So due to that, this will keep on move as the radius, as the resistance value increases. You could notice that the resistance value increases, which is in the denominator, will get the overall radius value smaller and smaller. So if the radius is 0, then you will get the value of 1, which is the outermost circle of the Smith chart. And the radius value keep on increases, this overall value will decrease. So for instance, if the radius is 0.2, 0.5, and as this resistance value increases, this value keep on goes down, and this you will get when the R value is infinite, you will get a 0. So which is given here as the dot at this particular point. When the resistance value will become infinite when it is open circuit. When the resistance will become 0 when it is short circuit. So these two edges can be done. So in between only all the impedances or at least all the resistance are going to be mapped. So this is mapped as a set of circles. Next we have imaginary part. So this imaginary part also has the very similar behavior, and this is actually described by the radius and the center. It is exactly orthogonal one. So because of that, you will get along the other axis. So you will get the circles like this. And we already know that the outermost circle is the maximum possibility that the reflection coefficient, the resistance part. So they have cut this other regions which are actually outside of the uh, the Smith chart. Okay, so they generally remove it. But if you notice some of the very advanced Smith chart, they will be still having this outermost circle, which they can play outside the Smith chart. So there are some circles will be available which we can ignore that part. So Smith chart has the outermost circle which describe the boundary of the Smith chart, which describe that the reflection coefficient equal to 1, where the impedance is equal to the real part of the impedance is 0. Okay, so these two, and this is the extreme case, and the 0 part, that is the center of the Smith chart, is going to describe the gamma equal to 0. Okay, so that is the center of the Smith chart. So like that we can easily describe this extreme ends of that. So in other words, what I told already, that the entire transmission line theory, which are described by means of infinite possible impedances, can be scaled to reflection coefficient, and this reflection coefficient can be scaled between from 0 to 1. So by this we can scale almost any impedances with this combination of real and imaginary circles. Just we have to make superimposition of that. When you superimpose this two, you will get the complex real and imaginary circles together will come. You can notice the real circles. These are the real circles and imaginary circles. So imaginary circles will come from outside and will come will go this way. Okay. So by this superimposition of the real and imaginary circles being done, and that is what we call as Smith chart. So by this, at for example, any particular value of the impedance can be placed here. So for that, what we have to do, we have to normalize the impedance. For example, I have a value of 70 plus j 50. Okay, so in that case I have to divide the value with the characteristics impedance. Let's say the characteristics impedance of the transfer line is 50 ohm. Okay, so this is the impedance of it, input impedance, let's say. So I have to divide it. So divide by 50. So when you divide by 50, you will get approximately 1. So it is 1.4 something. Okay, 1.4 plus j1. Okay, so we have to map it. How to map it? We have to search for the real circle with 1.4. So here you can see 1, here you can see 2, in between that 1.5. So this is the point. So here we have, yeah, we have to draw a imaginary, we should not use the imaginary, some circle. Okay, so uh, 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 illustration we have to do. Then we have to search for the one circle in the imaginary. So you can see here, so this is 0.5, this is 1. So this circle is having coincidence with this particular point. So this is the impedance point. We always should represent this particular point as the small one. Okay, it can be small input impedance or small load impedance, whatever it is, we can define that in this way. Okay, and we can even move this point. We will see on the way. Okay, so this is what we call Smith chart, and this Smith chart later means applied with various aspects. So now we have the modern standard Smith chart looks like this. So you can see the concentric circles, and it is very difficult with human eye to distinguish what is the point. For instance, for 1.4, I have taken 1 here, and here it is 2, and then it is approximated to 1.5. Then I have taken this value approximately as a 1.4. So it is very difficult to see. So that is what it is solved here. So when this point is moving along the x-axis, the small to help us to exactly pinpoint the real and imaginary circles, and to exactly locate the impedance or the reflection points. So this is how we have to use the impedance circles to describe any particular impedance. And in the bottom you can see some axes. These axes can be used for describing the same impedance and the reflection coefficient in alternate manner. For example, standing wave ratio, the standing wave ratio, and then extended standing wave ratio. Like that, several concepts are available, which are a little bit advanced version, which is not useful for us. But we will take only this voltage standing wave ratio. This VSWR can be calculated. So we already know that the VSWR will go from 1 to infinite possibilities are there. So 1 to infinite we can easily describe within this scale. By the way, if I, instead of defining this impedance, if I define the impedance value with 1.6, let's say, or 1.8, then I have to see 1.6, and correspondingly I have to map the particular point here. With respect to the center, I have to simply draw the circle, and this circle is nothing but the VSWR circle. VSWR circle tells the uh, exact location of the reflection coefficient with respect to the center point. So by the way, we can easily put everything. So instead of calculating using every time using this set of equations, Smith chart directly help us to map the uh, impedance, reflection coefficient, standing wave ratio all together in a one single system. Okay, since it is solving almost infinite possible problems, so it is people always refer this simple chart, very humble chart, as the more than a computer. So we can draw VSWR points and all the way. That is what we discussed here. Okay, now we will see how to use this Smith chart for various other applications. And another, as I already told, the impedance point can be mapped along the transfer line, and we can, so for instance, we already know that this is the load impedance, and at any particular point we can calculate the input impedance. So what is the expression for it? The input impedance can be nothing but, yeah, let me write it. So we have Z0, so that is the input impedance, which is nothing but Z0 ZL plus J tan beta L divided by okay, this is supposed to be Z0 supposed to come here. So Z0 plus J ZL tan beta L. So with respect to this equation, at any particular length we can calculate that. So instead of applying this little bit complicated equation, every time we have to apply beta and all, instead of that we can move along the Smith chart itself. If this is the point where we have mapped our ZL using this technique, using by calculating this normalized impedance, and we got the uh, normalized impedance, and we mapped here. Okay, using the proper scales we have mapped it. Like that we have mapped the ZL. Now if I want to move for lambda by 8 length, so what I have to do, lambda by 8 is nothing but lambda by 8 into, so which is, we have to calculate the beta L. So beta is nothing but 2 pi by lambda. So cancel the lambda, you will get 2 pi, so which is nothing but pi by 4. Pi by 4 is 90 degree. So we are going to draw a line, and we have to draw a orthogonal line along the 90 degree. So we already have we can have a circle, and the circle cross-secting point is nothing but the input impedance at length lambda by 8. And similarly we can go for lambda by 4, it is exactly opposite points. And again we can go for 3 lambda by 8. And another interesting thing is, when you close the point for 360 degree, which is nothing but lambda by 2. So when the circle closes by lambda by 2, the circle will keep on repeat. So this is the general property of harmonics, which we already discussed, that the impedance of the line will vary for every lambda by 2. So for every lambda by 2, the impedance will go from negative value to positive value, or positive value to negative value it will go. So that is what described here in this Smith chart, that for from the initial point to another lambda by 2 it will come. So this is another important advantage of Smith chart, that any particular impedance function can be defined within the scope of lambda by 2. When the value is greater than lambda by 2, let's say I have a value of 1 lambda, so this I have to subtract from lambda by 2. So I will get lambda by 2. For this particular lambda by 2, I have to map it. Otherwise, if I have the value of, let's say, 1.2 lambda value, so I will subtract the by lambda by 2, and once again it will be greater than lambda by 2. So I will subtract by lambda by 2. So which will result me 0.2 lambda. So 0.2 lambda means 2 pi by lambda into 0.2 lambda. So cancel it 0.2. So which will give 0.4 pi. So this I have to calculate in terms of degrees. Let's say this value is I don't know. Let me use the calculator. So 2 pi is 360 degree, 360 into 0.2. So which is nothing but 72. So I have to move for 72 degree. So I can pinpoint the location of the input impedance. Okay. So this is how we can use the Smith chart. Okay. If we take an example, we will easily understand it. Let's take an example. What we are going to do, we are going to recall the example 3. Okay. I believe you still remember the last class how we worked out and calculated this values. So we have taken a lossless transmission line which has the alpha equal to 0. Then we have the characteristics impedance 50 ohm and 30 meter. So length is given, and this is nothing but the frequency. So from now next we have ZL. So this ZL we have got now, and the transfer lines U, that is the phase velocity is given. Okay, so now what are the things asked? We have to calculate the input, the reflection coefficient, standing wave ratio, and the input impedance. The three value we have to calculate. We have used the very basic equation method. So we have calculated the reflection coefficient, standing wave all the way using this very fundamental equations. Also calculated the input impedance using this. Okay, so beta L is calculated using this omega L by U. So we got this, so 120 degree we got, and we substituted this here, and overall we calculated this input impedance. So this is the basic method, but the same method can be tried with the Smith chart. So how to do that? For that we have to take the Smith chart and we have to first map the ZL. So how to map the ZL value? First we have to say what is ZL. ZL is nothing but 60 plus J40, and this value is supposed to be normalized. So that is what it is done over here. So which is after normalization, we will use small letter for it. Normally we use capital letter for impedance. So now here it is used with small letter. You also always supposed to follow that. This is very strict representation, because we can't simply take a chance of this simple difference. So always you have to use capital letter for real impedance value, and the normalized one will with small z or small z, like that you can do. So we are dividing this, we got the value. Now this value is supposed to be mapped in the Smith chart. So how to map it? First we have to look at the real value. The real value is 1.2. Okay, so instead of capital R, let me use the small r. So small r is nothing but 1.2. The 1.2, this is the center point is 1, so they will be nearby. So this is zoomed here. You can see that. So this is 1 and this is 1.2. This is 1.4. I believe you can see that. So this is the 1.2 and this value is here. So this is the circle we are supposed to follow. Okay. Now next we have to look for the imaginary part, that is x. The x value is 0.8. So 0.8 approximately will come here, that is zoomed here. So you can see that the 0.8 is here. So where this value is 1 and 0.9, 0.8. So this is the point. Now I have to extend this line. And this meeting point is nothing but 1.2 plus j 0.8. So this is what the impedance point of the load, which we have mapped in the Smith chart. So that is what clearly shown here. Okay, so I believe you got it. Now once we mapped, then we can easily calculate the reflection coefficient all the way. So how to calculate the reflection coefficient? the easiest way to calculate the reflection coefficient is from the center to this, what is the total distance, the radius of this particular point. Okay, so that is nothing but the that is the reflection coefficient with respect to the radius of the Smith chart. So the radius of the Smith chart, many people used to confuse. You can see there is a innermost circle. So this innermost circle is the radius of the Smith chart. Outside there are three scales will be there. They are not belongs to Smith chart. The innermost one. So it is very natural that you're supposed to calculate the radius of the Smith chart. So you can use this axis and you can calculate the value. Okay. So every time whenever you get the Smith chart, first thing what you have to do, you have to calculate the radius of the Smith chart. Okay. So for instance, in our in VIT, when they give the Smith chart in the term and exam or something, they will give Smith chart with radius of approximately 8 centimeter. In some brands you will see 8.2 centimeter. So you don't take any risk, always use the scale and calculate the radius of it. Now this distance and take the ratio. Let's say this distance is m and the Smith chart radius is s. So the reflection coefficient is nothing but m by s. So that is what the reflection coefficient. So this can be easily done with a simple scale. So how to map the reflection coefficient? So we already know the this is supposed to be 60. Okay, so we already know the ZL, so we can easily calculate the reflection coefficient. We already calculated this value. So this is what the value mapped at this particular point. So the value is, magnitude is 0.3523. So what is the value is the relative distance of the reflection point or the reflection coefficient in the Smith chart. So for that, what we have to do, we have to calculate the radius of the Smith chart. So this radius of the Smith chart, let's say this is 8.2 centimeter. Then 8.2 centimeter into 0 point, this magnitude 0.3523. So whatever the value it is coming, we have to note down that. Let me calculate the value. So 8.2 into 0.32, sorry, 3523. So this value is nothing but 2.88 centimeter. So 2.88 centimeter is very difficult. We will map it to 0.29 centimeter. So in the scale, actually you will take with compass, and what you have to do, you have to choose the center point, and with respect to that you have to draw the circle. And this circle is nothing but what we referred as Vswr circle. So you have to draw a circle. It's not very perfect, but this is how we have to draw the circle. Now we have drawn the circle, and in this circle any one of the point is going to be the final reflection coefficient. So how to put it? We have to use the angle. The angle is 56 degree. So this is the angle 0 degree. So from here we have to go for an angle of 56. So how to exactly map it? It is very easy. So if you notice the outermost scales of the Smith chart, you can see that there will be degrees will be mentioned. You can see here 0, 10, 20, 30, 40, 50 is there, and 56 you have to draw a line, and just you have to draw a line. So this circle and this line which is meeting at this particular point, which is nothing but the reflection coefficient, and this is the same point as the ZL. Let me put as a small ZL. So ZL. So you can map the initial reflection coefficient or the impedance, whichever is known first. You can easily map it. You have to use you have to take the value, normalize that, find the real and imaginary circle radius, and map it here. So this is very easy method. The next method, or most commonly preferred method, in fact many people directly will calculate reflection coefficient rather than impedance. So for them, this is the method they have to follow. So they have to calculate the value of the one with the magnitude and the angle of the reflection coefficient. So this two values known. So this value should be multiplied with the radius of the Smith chart. Then this value should be drawn as a circle. Then using this angle, we have to take a line. So this line joining and the circle will, sorry, the circle line joining point is nothing but the impedance, sorry, the reflection point, the reflection coefficient, load reflection coefficient, which is again nothing but the same point as nothing but the impedance. So in Smith chart, the reflection coefficient is nothing but the normalized impedance. So this is a thumb rule. So I believe you got it. Now what is the next problem is we have to calculate the input impedance, from the load at 30 meter. So 30 meter length is the physical length. When we multiply with beta, we will get the electrical length. So the beta value is nothing but omega by u. So omega by u is calculated using this value, and the 30 meter is applied here. So we got the value of pi by 2 pi by 3. And in many places, this length will be defined in terms of lambda, like lambda by 4, lambda by 2, or 0.5 lambda, like that it will be defined. Okay. So now we got 120 degree, that is the electrical length. So the first the second method is we have to calculate the lambda value, and we can calculate the physical length. So just we have to divide the overall 30 meter with lambda, you will get lambda by 3. So the lambda by 3 is 120 degrees. So you can calculate by either means. So this is a very common method people used to follow. So we got it. So beta L we got. So this beta L distance we have to move. We already know that the 56 degree, how it is plotted. We have taken a scale, we have moved 10, 20 and up to 50. This is 60. In between that, this point is selected. So this is the 56. This is the initial point of the impedance. Now we have to just add 120 degree with that. So when you add 120 degree, you will get 176. So here to here 176 we have to search. So this is actually 0 degree, and this is actually 180 degree. So 180 degree, just we have to take 4 less, you will get 176. So this 176, when you draw a line, this is actually meeting at this particular point, and this is the impedance point which we moved from this to this. In other words, I should say that there is a load, and in this load is connected with a 30 meter long transmission line. And after this 30 meter length L, now we have to calculate what is the input impedance. So this input impedance simply can be mapped from this point to this point by taking this 120 degree extra, which is 176 degree, and we have pinpointed this location. Now we have to see what is there. Okay, so how to see that? We have to zoom in. Okay, so when you zoom in, you will see that this is actually 1, and the values keep on decreasing. So this is 0.3, 0.4, this is 0.5. So in between that, so the typical values, real values 0.47, and here we have to see the points like 0.1. Okay, so in between 10 subdivisions are there, and this 10 subdivision, it is going along the way of 0.03. Okay, so this is actually best value which is taken with the human eye. Okay, so it may be correct or it may be wrong, so that is not at all a big problem. So this is the best observation what you have done. Okay, so once it is calculated, now we have to multiply this value with the Z0. So Z0 is 50 ohm. So 50 ohm and this value we are going to multiply. So this value, when you multiply, you will get the value. You can notice that this value and the value which is calculated using this one very close, but this one is the accurate one. Why? Because this is calculated all the way by using calculators, and this one used with the Smith chart. So it is somewhat approximate one. You no need to worry about that. each and every student will get different answer. If they get correct answer all the way, then they copy it. So this is one smart way we used to do, find out that that student copied or not. Most probably student used to do this mistake. I have revealed to you now, so you just be smart enough. So this is how the Smith chart should be used. Let us take another example. So here we have a 70 ohm lossless line. So what is the meaning of that? 70 ohm line means the line has the characteristics impedance of 70 and it is a lossless line. So alpha equal to 0. And most probably 90 percentage or 99 percentage or even 100 percentage sure that you will always get the transmission line with lossless lines. So and has the uh, voltage standing wave ratio, that is VSWR, as 1.6, and the angle of the reflection coefficient is given as 300 degree. So if the line is 0.6 lambda long, obtain the reflection coefficient, load reflection coefficient, load impedance, and this problem we will see in the next class. So the given values are nothing but Z naught, S, angle of the reflection coefficient, and length. These four values are given. Okay. Now we have to solve the problem using Smith chart. So what we are going to do? First, we are going to draw the uh, this so-called S circle, okay, or the Vswr circle. So how to do that? The value is given as 1.6. So if the value is 1.6, you can use the scale. In the very below there will be a scale. The scale will start from 1 to infinite. It will go. It will slowly vary like 1.2, 1.4, 1.6. So you have to take this value in terms of the compass and you have to draw the circle. So this is the very common method people used to follow. And if you cannot observe that, the alternate method is you have to calculate the reflection coefficient. The magnitude of the reflection coefficient in terms of VSWR is this formula. So we are going to substitute, and when you reduce the value, you will get this. Now this is the magnitude of the Smith chart. So what you have to do, you have to multiply this value with the radius of the Smith chart. You can notice here this is the magnitude, this is the radius. When we multiply, we got the value of 1.9 centimeter. So this 1.9 centimeter circle is mapped. Okay, so now we got the reflection coefficient, magnitude, and we got the VSWR circle. Now we have to place the impedance point. For that we are going to use the angle. So how to use? We have to use this angle 300. So I already told that this is the 0 point. From this we have to move along this path and we have to take the 300. So 300 is very easy. You just search for the 300. So this is, we know that it is 180, and then we have here and uh, here we have 200, and here we have the 300 is here. Okay, yeah, 300 is here. So first you have to put a point here, and with respect to the center you have to draw the line. Okay, so don't simply take the scale and don't do it. First always mark the points and draw it. So this meeting point is nothing but the reflection coefficient, and the same point is nothing but ZL. Okay, so we can easily calculate the value. So just you have to pinpoint the location. So with respect to the center point, so first you have to extend this particular point to let me zoom that. So let me delete the other points so that you can see. So you can notice that this is the point where we have let me use some other color. So you can see that this is the point which we have noted as a gamma. Okay, and this is the same point which is nothing but the small z. So from this particular point, so we have to move this particular point to find out the real point. So this is actually, so you can notice that this is 1.2, and this is 1.1. So it is 1.1 something, 1.15, let's say 1.15. So let me write, this is 0.115. So this is the real point. And how to calculate the imaginary point? So you can notice that this particular point is traveling along this circle point. So you have to keep these two lines as the reference, and you have to keep on moving. So here also you can move this particular point slowly. So this is the tricky part. So you have to do it very slowly, and you got this point. So this point is, this is actually 0.5, this is 0.4. So it is approximately 0.48. So this is nothing but the x value. So from this we calculated the uh, r value and x value. Okay, so once r value, actually this is 1.115, so both the values are calculated. Just we have to multiply with the characteristics impedance. So here characteristics impedance is given as 70 ohm, so we have multiplied and we got the value. So this is the ZL value, and we can calculate the mode point in the next class. It's already too late, so we will see in the next class. So please attend this class little early tomorrow, so that I will yeah. Thank you so much. We will see in the next class. It's already too late.
Sir, sir,
Yes. Yeah.
yes, sir. I had to talk to you about something, sir, regarding the final year project. Do you have a minute?
Yeah. Maybe after the class you can call me. If you have time, you can call me after the class.
Okay, sir. Okay, sir.
Okay. We will see in the next class. Thank you.